Evaluating a machine learning model refers to measuring something known as generalization capacity of the model. Now, if you remember the elephant and the blind man story, then here's the picture that summarizes the story. Then combining, let's say, all the six blind men, let's say combining the knowledge of all six of them is, say, for example, combining it's a spear, it's a fan, it's a wall, it's a rope, it's a tree, it's a snake, is more like optimization. Now, a deep learning model can, in a way, learn that it is, say, for example, provide weighted six blind men, let's say, weighted, such that maybe it's more of a rope and very less of a spear and a wall, etc. So based on this color, you can see that wall is faint, rope is bold. So we can, in a way, weigh the knowledge of these blind men to come up with overall idea about what exactly the input data is. So here elephant is our input data, and understanding that it's an elephant is the outcome that we want. Now optimization is more like having a lot of blind men and who understand many aspects of the data from a different viewpoint. For example, one blind man may think that the data contains something, the other blind man may think that the data contains something else, and so on. So the process of merging this understanding of many blind men is something called optimization. We can compare this with optimization. What we instead want the model to do, or at least aim for, the bigger aim, is generalization. That is, we want the model to understand that given this data, there's an elephant there. So elephant, such that it's an elephant, of course, it's like a spear, it's like a fan, it's like a wall, but it's an elephant in which the model understands that one side is a snake-like tail and the other side is rope-like, and so on, right? So overall, our goal when evaluating a machine learning model should be to measure this ability of the model to generalize. And the goal in machine learning is also, of course, we do optimize. I mean, this is exactly what we do, right? Gradient descent is an optimization algorithm, and we basically optimize. But the higher goal is actually to generalize. The goal is to achieve models that generalize. So overall, models that perform well on never before seen data. And this is exactly why we split our data into three sets. We split the data into training set, validation set, and test set. The reason why we do this is every time, say for example, our training experiment 1, so experiment 1, we take the training data to build a model, and then we use the validation data to check the model. Let's say we got an accuracy, maybe on the training set we got 99% accuracy, and maybe on the validation set we only got 80% accuracy, right? So then we do another experiment, experiment 2, and change a few things in our model, and maybe this time, let's say the training accuracy goes down, maybe 98%, but let's say the validation accuracy goes up to 85%. Okay, we know that we are doing something good, right? Now remember, we are not actually using the validation set to do the training, so not used for training, but we are using it to pick the best model. So even though we do not directly use validation dataset to do the training, there is something happening here, something known as information leak. Information leak from the validation set to your training model, leak to the training process, So even though at the end of the day, you may claim, well, I never used any of the validation set to do the training. So did not use validation set for training. But however, your rationale that evaluation data set was not used for training and can be used for evaluation is wrong, because we are selecting the best model or tuning our hyperparameters based on validation data set. So for exactly this reason, what we want to do is we want to split the data into development set and test set, and never actually touch the test set during development, and use this at the end of the day after all our training is done and validation is done to finally report the accuracy or performance of the model. Now, there are a few interesting things, particularly those concerning how do we evaluate our model, that is, topics related to evaluation protocol. The first thing that we want to consider when evaluating a model is data representativeness. That is, when we split our data set, say we have all of these rows, when we split our data, how well or how representative is our training set and test set? So if this is our test set and if this is our training set, how representative are they both, right? So maybe the training set is very representative, but maybe the test set is not. So we want our training set and test set both to be good representative of the data at hand. One example is, say on the Paima Indian diabetes data set, where we are predicting whether or not somebody has diabetes, what can happen if we don't shuffle the data? So if in our data rows, let's say all the positive values, are in the first rows and all the negative values are in the bottom rows, then if we randomly select this data set to do the training and the remaining data set to do the testing, that we only have maybe negative examples in the test set. So we want to make sure that we shuffle the data to have good representativeness in both the training set and test set. The next important thing that we want to consider when evaluating a deep learning model is the arrow of time. Say in your data set, what you have is data collected over time. So in x-axis you have time, and here you have your data points, right? So maybe you have, let's say, 1,000 examples like these, and in order to train and validate, you shuffle these examples, and then pick maybe 10% for testing and remaining 90% as a development set. Now, if we are trying to do this, that is trying to predict the future given the past, for example, we want to predict tomorrow's weather given previous weather, you should not randomly shuffle your data before splitting it. This is because doing so will create something known as a temporal leak. That is, information from the future can leak into the past in your training model. So if your model during training already sees some examples of tomorrow's weather, then of course the model will do well tomorrow as well. So the good way to do here is to split the data into training and validation or training and test, such that the test contains maybe a good portion of only future data, and the training contains a lot of current and maybe past data to learn from. So all we have to do is make sure that your data is posterior to the data in the training set. So whatever is in the training set should be before what we would like to test the model on. The next thing to consider when evaluating a model is to check for redundancy in data. Now, the data in the real world, it is very likely that there may be data points that appear twice. For example, maybe you took the same picture many times, and upon the random splitting, so if we have a lot of redundancy, and let's say 70% is in training and 30% is in testing, then many of the examples in the training set may already be in the test set, or many of the examples in the test set may already be in the training set. So then if we evaluate on the test set, when we evaluate, we'll get a higher accuracy because these examples are already in the training set. So in effect, what we are doing is we'll be testing on a part of our training data. So if our data may have a lot of redundancy, we want to make sure that the training set and the validation set are disjoint. Finally, let's summarize the evaluation metrics commonly used for evaluating machine learning or deep learning models. For classification problems, the commonly used metrics are accuracy, precision, recall, F1 score, and area under the curve. Out of all of these metrics, if I have to choose one metric, one single metric to evaluate a classification method, then I would choose F1 score because it is in a way representative of all the scores. All of these metrics, accuracy and precision can, or even recall, can be sometimes deceiving because sometimes the accuracy may be high, but the recall may be low, and so on. Something that we want to keep in mind is in case of binary classification, the baseline accuracy is more than 50%. So if you have a data set where, let's say, most of your examples, let's say 80% of your examples are positive labels or ones, and 20% of your examples are negative or zeros, then your baseline accuracy is already 80%. So if your model here gives you 81%, then there's no reason to be happy about this model because this is barely above the baseline accuracy. Now, baseline precision and recall can also be 100% depending upon how we evaluate. Your model may be very precise and give you precision values of 100%, but its F1 score or recall may be lower. So for that reason, accuracy and precision alone are not good metrics to evaluate a classification method. For a multi-class classification method, similar metrics exist, that is accuracy, precision, etc. But the baseline accuracy here is lower and it depends on the number of classes. For regression problems, when we are predicting continuous values, evaluation metrics commonly used are mean absolute error, mean squared error, log of mean absolute error. A really helpful tool when a model is predicting continuous values in a regression problem is to plot a scatter plot or histogram, a plot of the distribution of MAE. That is, maybe we can look at how the MAE are distributed, maybe between true and predicted, and so on.